Last episode, we saw what happens when a system isn't designed for scale. Your app goes viral, users flood in, and everything crashes. One of the biggest challenges faced by engineers in big tech is scalability. It's one thing to come up with a clever algorithm or system, but yet another to build it in such a way that it can handle thousands of transactions per second and petabytes of data. Whether you are dealing with 1,000 users or a million users, your system should be performing efficiently. Today we'll break down the exact strategies, from vertical and horizontal scaling to a lesser-known but practical approach called diagonal scaling, along with the trade-offs to consider when choosing the right approach. Episode 2. Scaling from 0 to millions. So what exactly is scalability? Simply put, scalability is the ability of a system to handle increasing amounts of work gracefully, without breaking, slowing down, or becoming unreliable. It's not just about adding more users. It's about making sure your system can maintain performance, availability, and reliability even as load increases. Think of scalability as your system's growth potential. Most systems start small. A few users, manageable data, predictable traffic. But as they grow, so do the demands. User-based growth, your app goes viral. Data volume increases exponentially. Peak events like Black Friday spike traffic 10x in seconds. If your system can't scale, it crashes. And you can't meet performance SLAs like responding within 200 milliseconds without scalability. So let's start with the first approach, vertical scaling, also known as scaling up. This means adding more power to a single server, more CPU, RAM, or disk space. Essentially, vertical scaling means getting a bigger box. The big advantage here is simplicity. No need for distributing data or syncing across nodes. Your application doesn't even know it's running on a bigger machine. Also, with vertical scalability, the migration is fairly simple. You just upgrade the hardware and you're done. No distributed coordination, no replication, no sharding. If you have a really small application that doesn't get a whole lot of traffic, maybe vertical scaling is enough. You just throw a bigger virtual machine at it and it solves the problem. It's cheaper, faster to deploy, and easier to maintain early on. But here's the ceiling problem. Servers only come so large. You can only get so many CPUs in a system, there's only so much memory. At some point, you're going to hit a wall. High-end hardware gets very expensive, and more importantly, your system is still a single point of failure. If that one server goes down, it's going to stay down until you can replace it. So vertical scaling only gets you so far. That's where horizontal scaling comes in. Instead of upgrading one machine, you add more machines and distribute the load across them. Scale out, not up. This is the foundation of most cloud-native architectures. The idea is that instead of a single server, you have multiple servers with a load balancer distributing the traffic. If one goes down, the load balancer reroutes traffic to the other servers automatically. No downtime. Need more capacity. Just add another server to the fleet. There's practically no limit to how much you can scale this way. At Amazon, it was routine for servers to handle tens of thousands of transactions per second. Modern techniques allow you to horizontally scale such that if you get more traffic, you just throw more servers at it. This is how systems like Netflix and Google operate, running thousands of servers distributed across the globe. But horizontal scaling brings in a lot of complexity. You need load balancing, state management, data consistency, and service discovery. The catch is that your servers must be stateless, meaning any server can handle any request at any time without assuming it served that user's previous request. It's more powerful, but it requires thoughtful architecture and operational excellence. So every scaling decision is a trade-off between cost, complexity, and performance. Vertical scaling starts cheaper and is simple, but it has limited growth and creates single points of failure. Horizontal scaling allows for parallelism and redundancy and can serve many concurrent users, but comes at higher operational cost. Choose the simplest architecture that meets your projected requirements, but no simpler. And that brings us to diagonal scaling, the best of both worlds. You start by scaling vertically because it's simple and cost-effective early on. Then, as your system grows, you scale horizontally to handle the real load. This approach is very common in cloud-native apps because it gives you early simplicity and long-term scalability without wasting money up front. Most organizations prefer diagonal scaling. But here's the thing. Traffic isn't constant. You might have a spike at 9 a.m. when everyone logs in, and almost zero traffic at 3 a.m. Why pay for 100 servers when you only need 5? That's where autoscaling comes in, the engine behind elastic infrastructure. Autoscaling is the automatic adjustment of compute resources based on current system load. It uses metrics like CPU usage, memory consumption, and request rate to trigger scaling. There's reactive scaling that kicks in when thresholds are crossed, and predictive scaling that uses historical data to scale in advance. AWS, Azure, GCP all support it as a first-class feature. Smart autoscaling isn't just about staying up, it's about staying cost-efficient. Let's bring this together with a real-world example. Twitter early on ran as a monolithic app. Fine for limited users, but as the user base exploded, they hit performance and reliability issues. So they moved to horizontal scaling, breaking the monolith into microservices, adding load balancing, caching, and distributed databases. This shift allowed them to handle massive global traffic with resilience. The lesson? Don't over-engineer too early, but don't wait too long to prepare for growth. To recap, vertical scaling is getting a bigger box, simple but limited. Horizontal scaling is getting more boxes, powerful but complex. Diagonal scaling combines both, starting simple and scaling as you grow. And auto-scaling adjusts dynamically to traffic for cost efficiency. Your scaling approach should evolve as your system and user base grows. But here's the question. When you have multiple servers, how does the traffic know which server to go to? That's load balancing, covering types, common algorithms, and how cloud platforms handle traffic distribution. It's the topic of our next episode.